Hello, my name is Alex Davis. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. Today I'm going to be talking about estimation of social welfare functions for consensus. All cardinal and fully comparable social welfare functions have the same form. There are some trade-off between the mean of the utilities of decision makers, U bar, and a homogeneous degree 1 function of the difference between the utility functions and the mean. The level sets of the social welfare functions look like this. Basically, they are cones with different angles depending on whether decision maker 1 is advantaged relative to decision maker 2 or vice versa. Our idea is to estimate the social welfare functions is to do the following. First, we fold our observations over the y equals x axis. We fit a weighted regression to those observations, where observations that had to be folded get lower weight. We fit a separate weighted regression where observations that did not have to be folded get a lower weight. And finally, we reflect back and make predictions in the original space. So our weighting function is the Gaussian tau kernel. Call order A some order, call order B a different order. And we're just going to construct a distance matrix that counts the number of inversions of the orders between A and B. We then apply that to the Gaussian function. So our approach is to fix a reference order, reflect all coordinates into that order. The number of coordinate switches is the Kendall's tau distance. And for each unique order, we're going to conduct a weighted linear regression where observations get more weight if they're closer in the Kendall's tau space. In 2D, we'll look at level curves in a simulation. Each group is represented by a single alternative and is presented a single alternative and votes yes or no on it. The underlying social welfare function here is going to be the min, where x is the alternative or the social state. U of that social state is between 0 and 1. It's assumed to be known for all decision makers. And if the social welfare function is greater than the median of the social welfare functions in the simulation, the group votes yes, otherwise no. This is what the level curves of the weighted sum estimator look like. We can see that they're straight lines where the angle depends on the data. The Gaussian kernel regression is a more flexible function, and we can see that it's just curvy functions that don't necessarily look like the true cardinal fully comparable function. The mean variance trades off between the mean and the square root of the variance with one parameter k hat. We can see it does quite well in 2 dimensions. And again, here we have GTK as described earlier. As we add more decision makers, we can see what happens. For the small sample simulations, we'll have 15 choices and 4 to 7 decision makers repeated 10 times. For the large sample, we'll have 200 choices with 7 decision makers. And our criterion is the rank correlation between the fitted social welfare function and the true social welfare function on 1,000 choice sets that were held out. So if we look at the min function, our results in the small sample, GTK does the best, followed by mean variance. For large sample, GTK, again, does better than mean variance, with a correlation on with 200 choices between GTK and the test set is approximately 1. Here's what the data look like for the small sample, 4 and 5 decision makers, 6 and 7 decision makers, and here's 200 observations. When we look at the mean function, we can see that the mean outperforms the mean variance, outperforms weighted sum, outperforms GTK. For the large sample, they're all fairly equivalent, where again, the rank correlation is approximately 1 between GTK and the test set. Here's 4 and 5 decision makers, 6 and 7 decision makers, and 200 observations with 7 decision makers. Here we have gamma equals -1/2, a trade-off between the mean and the min. Here the mean variance outperforms the mean, outperforms GTK with small samples. With large samples, GTK outperforms the mean variance, outperforms the mean. Again, the rank correlation in the large sample is approximately 1. 4 and 5 decision makers, 6 and 7 decision makers, 200 observations. In summary, GTK is the only method that has the right large sample properties with rank correlation of approximately 1. In small samples, mean variance does quite well. It has only 1 parameter. GTK and mean variance can perform reasonably well with few observations. Kernel regression does not put nearly enough constraints on the function space. I'd like to thank Niles Guo, Professor Megan Mauder, Professor Destiny Knock, and the NSF.